Okay, kids, welcome back to the in-school session for applications of sinusoidal functions. So today, this is going to be the final lesson in this unit. We're going to look at why we bother spending so much time studying trig equations, graphing them, and solving them. So this puts it all together. This is actually a really interesting little unit here, and let's look at it. So the idea here is periodic circular motion. We are going to be looking at all sorts of periodic circular motions. That's things that keep spinning around in a circle. If you have something moving at a constant speed and it's going in a circle, quite often we can describe it with a sinusoidal function. So for example, if you were riding a Ferris wheel and you were sitting here, and here you are in your chair, look at how much fun you're having in a Ferris wheel. That's a big smile on your face. There you go. There you go. There's a smile sitting on top of your face. What we could usually describe your height with is an equation that looks something like this. So your height, h, as a function of time, equals a sine b, t minus c plus d. H would be your height off the ground, t is your time, a radius of the wheel, b is the height of the center, d height of the center, b and c related to the period and the starting point, blah, 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 blah. Okay, so this equation is not necessarily going to make any sense right now, but we're going to use something like this to solve all sorts of problems, and I'm going to do my best to explain why the heck it comes in this form. Also, why is a the radius of the wheel, why is b the height of the center, and so on. Okay, so just a little thing before we jump into it. Why the heck do we use sine to describe the motion? I'm going to show you this, and then I'm also going to show you a nice little GIF to hopefully explain the whole thing. So if we wanted to figure out the vertical distance from the center, what we could do is we could think of if you were here, like let's say you're on a Ferris wheel. It's not always a Ferris wheel, but sometimes we'll have a Ferris wheel or some other sort of spinning thing. You're right here. How high are you off the ground? Well, we'd first start by figuring out how high are you, so what distance y are you from the center line? If you rotate around like this, then we could calculate your height by using y equals a sine theta. And more fundamentally, remember sine theta is opposite over hypotenuse, so that would be y over what we're calling a. Now a happens to be the radius of the wheel, which is what I said up here. So we're basically just saying a is the radius of the wheel. Now we also know that a is a vertical stretch and a is also amplitude. So why is the radius of the wheel equal to the amplitude? That's another thing worth looking at. But right now, let's just focus on this. So what we can say is since the angle theta is constantly changing over time, and this is something that would happen if you're just rotating around at a nice constant speed like most Ferris wheels. I don't know about too many Ferris wheels that start to accelerate or slow down other than at the start and stop. Then what we can say is that the time and the angle are proportional. So I know we're kind of saying y depends on the angle, but we could also say y depends on the time. And when we say something is proportional, there's some sort of a scaling factor. Those of you who have taken physics know that if you're traveling at a certain speed, distance is proportional to time, and the constant of proportionality is speed or velocity. So velocity is the thing that converts time into distance and vice versa. Similarly, we're going to have a more general thing here where we're going to say the angle changes as the time changes, but there's some sort of constant of proportionality in there, b. The rest of the equation with the c and the d, well, the d is simple because the d kind of tells you like how high are you off the ground, right? At sort of a neutral position, like here and here. So that's like your center line. And then c is, of course, do you start up high? So is your graph going to start at its highest point and then maybe look like cosine? Is it going to start in the middle and then maybe look like sine or whatever? So that's like your phase shift. I think this is going to be a little better explained also by just seeing a nice little image. So this actually shows it pretty well. When you're going around in a circle, you can see here you're traveling around in a circle. Your height is fluctuating like a sine curve. So at any moment we can calculate how high you are, and we can plot that as a function of time, and it's going to make this nice little sine curve. You can see that where the center of the Ferris wheel, or whatever it is, the center of the Ferris wheel corresponds with the center line of your graph, so that's what d has always been. The radius of the Ferris wheel is what corresponds to the amplitude, so that's your A. And of course, depending on where you start and stop, that would be like your phase shift, because some graphs will start high and some will start in the middle and some will start low. And then B is, of course, how slow you are going around in a circle, or how horizontally compressed your graph is. If you slowed this down, this rotation, your graph would get expanded out horizontally. So just keep in mind, you just have to understand the basic structure of this equation, why it's sine, and then for everything else, we'll just understand that anything moving in a circle, doesn't have to be a Ferris wheel, could be anything, but anything moving in a circle is usually going to have its position or its height looking like some sort of a sine wave. Okay, so hopefully that all makes some sense to you. If not, well, no one likes to say this, but there's a formula, and let's just use it. Sometimes that's okay, because that also helps it make sense later on. Okay, so anyway, let's look at example number 1. A Ferris wheel with a diameter of 50 meters rotates once every 2 minutes. A passenger gets on at the lowest point, which is 4 meters off the ground, and then begins the ride. So you've got this Ferris wheel sort of thing. This is a terrible sketch. I'm just giving a rough little thing. They're going to get on here at the lowest point, and then they're going to start spinning around and around. I don't know if it's clockwise or counterclockwise. I don't really care. It doesn't actually really matter. But now we want to convert this into how high are they? What is their height as a function of time? And they're going to start at the lowest point, so it's going to be down here. And then as time goes on, they're going to go up and up and up. And then they're going to reach like the highest point, which corresponds to here. And then they're going to go up there, and then they're going to start to come back down, so then their height's going to drop. And they're going to wind up having a graph something like so. So that was a really terrible graph. Maybe I'll just do a slightly better job of it. So when we say sketch, the detail is sort of ambiguous, but you know, let's get some actual numbers in there. So let's start by doing this. Let's actually do a little, there we go. Okay, so here's time, here is height. So they get on the lowest point, which is 4 meters off the ground. So if I'm calling this 0, then the lowest point is going to be at 4. And that's going to start at t equals 0. So what we could do is we could even use function notation. We could say height at time is equal to 0 is equal to 4. So right there, we're going to plot a point, and we're going to say that our height at time is equal to 0 is a height of 4. Okay, so then what we're going to do is we're going to then, of course, use our brains here. We're going to say the Ferris wheel has a diameter of 50 meters. So what's the maximum height you can get to? And all of you at home saying 54, good for you. Because if it's got a diameter of 54, then the highest you're ever going to get is diameter of 50. You're only going to get 50 higher than 4. Okay, so anyway, it rotates once every 2 minutes. So that means at 2 minutes, you're going to be back here at 4. And at 4 minutes, you're going to be back here at 4, and so on. They get on at the lowest point, which is 4 meters, and then they get to ride. So sketch a graph. So we just have to put the rest of this together. So what we have to do is, of course, we have to acknowledge that A is equal to 25, because this is the radius, equals half the diameter. We could maybe use a calculation or common sense to say D equals 54. 54 plus 4 over 2, so that's 58 over 2, so that's 27. So we can figure out that halfway in between these 2 points is 27. So that's going to be our center line. So we go dot, 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 dot. When we are told it rotates once every 2 minutes, that is a reference to the period. So remember, B equals 2 pi over period equals 2 pi over 2 minutes. So pi would be the B. And then C, of course, this is the phase shift, and we got to think about this. So we're going to say C equals, well, there's a couple ways we could do this, but I'm going to go ahead and say 0. I'm going to say no phase shift if cosine is used. So remember, the idea here is that you could use sine or cosine, but I'm going to use cosine because we're starting at our lowest point. I'm going to fill in the rest of this graph here. So right up here at 1 minute, we should be at a height of 54. Here, again, we'll be down there, up there, down there, and so on. And we're going to be drawing just a general sort of cosine graph. Okay, well, that's why we're sketching this, because it's not going to be perfect, but it's going to be good enough. Okay. So that's a pretty decent graph. Now I'm saying C equals 0 if there's no phase shift. And I'm going to actually just add one thing here. I'm going to write if negative cosine is used, because we can see that this looks like negative cosine of t. Okay, so there's my graph, and of course B says determine an equation. Now we've done most of the heavy lifting, so we'll just go ahead and we'll say y equals, so I'm going to use cosine as my main form. I'm going to use the variable. In fact, let's not even use y, let's use h. H is a function of t. And then I'm going to use the variable t, and I'm going to go minus c, and I'm going to go plus t. Okay, so it's not always sine, but in this case it's cosine. So we decided it's going to be negative cosine, so I'm going to write negative 25 cosine. We know that b is equal to pi, and we know that t is my variable. C is 0, so I can go ahead and close that up. I don't need parentheses. And d would be 27. So I've got negative cosine pi t plus 27. And if I put any number in for t, I should be able to get myself the height. So one thing we could even do is we could go ahead and we could test this. We could say, what if let's go over here, let's turn this on. Let's make sure we're in the correct mode. By the way, which mode should we be in, radian or degree? Because our variable is time, it's going to have to be in radian. So that's actually worth mentioning as well. So variable is time, therefore need radian mode. Okay, so what we should be able to do is when we've done this, we should be able to go negative 25 cos, and then we're going to go pi times, and if I want to know, let's say, the height at 4 minutes, just to pick a number randomly, I can go pi times 4, and then I'm going to go plus 27. And if I push equals, I get myself an answer of 2. So how high should this person be? And I realize I just made a mistake. It's not 27. It's supposed to be, this is actually supposed to be 29. So I realize I made a silly mistake, because what I did is up here, I went 54 plus 4 divided by 2 equals 27. That was completely wrong. I tried to do 54 divided by 2. It's actually 29. So my apologies to those of you who noticed there was a mistake. There absolutely was. That's supposed to be 29. And this is why it's a good idea to check your work. So if I use my proper equation, negative 25 cos 4 pi plus 29, I get 4. Does it make sense that my height is 4 at 4 minutes? When I look at my graph, there's the point, 4, 4 minutes and 4 meters high. Okay, so everything works out, life is good, and I've got all my numbers right, so I'm pretty happy with that. Okay, so question C, or part C says, assuming the ride lasts for 6 minutes, determine the times at which the passenger is 40 meters off the ground. Okay, this is actually a fairly challenging question, so let's first figure out some things. The ride lasts for 6 minutes. This is going to restrict my domain that t is between 0 and 6. Determine the times at which the passenger is 40 meters off the ground. So what I'm doing is I'm going to say the height equals 40 meters. And this is going to turn this equation, h equals negative 25 cos pi t plus 29, and I'm now going to have to solve this bad boy. So this is where it gets a little trickier because now I have to solve an equation, and it's not a nice equation. You guys are probably used to solving stuff like cos x equals root 3 over 2, and you can do that. Now I've got something much more complicated. It's not that bad, it just looks scary, but let's follow our general ideas here. So if we're going to solve this, we're going to want to isolate t. That's what we want to isolate. So the steps we're going to do that is we're going to first subtract 29, top and bottom, or side, left side, right side, never mind. So this gets me 11 equals negative 25 cos pi t. Then we're going to want to isolate cosine by dividing both sides by negative 25. Those are gone. And here we're going to get, and this is where it actually makes some sense to use your calculator, so we're going to go 11 divided by negative 25. And we're going to get, okay, so that's going to be negative 0.44 equals cosine pi t. All right, so how do we solve this? Does this look like a special angle kind of triangle thing? And the answer is absolutely not. So what we're going to do is we're going to go pi t, and we're going to figure out the reference angle. So this is where, if you want to figure out your variable, we're going to go inverse cosine. We're going to have to use our calculator, and we're going to ignore that negative sign and just take inverse cos of 0.44. So we're going to go inverse cosine of 0.44 equals. Okay, so remember, when you do this, you are getting pi t ref. Now this guy here, remember him, deal with those coefficients. So deal with coefficients, this is from a couple lessons ago, deal with coefficients at the end, the very end. So you're going to pretend like that's not even there. You're going to get your reference angle is 1.115. And then later on, you're going to divide by that pi. Okay, so keeping in mind sort of what's going on here, let's make a little graphical picture here. Here's my angles, and we have a reference angle of 1.115 radians. And remember, cosine was negative. So here, this negative sign right there, that tells me we're in quadrants 2 and quadrants 3, because cosine is negative in those quadrants. So what we have is we've got a reference angle of about 1.115 radians in quadrant 2 and 3. So that means this. So my angle, pi t, could be that, or it could be this. So we've got two different possibilities. So it's kind of weird because you're so used to thinking about angles, and now we're thinking about time, and time and angle are related to each other, so try not to get too worried about that. We're going to go ahead and finish solving this, and then you can see how things work out. So in quadrant 2, pi t, the actual answer, is going to be, remember, it's going to be pi minus the reference angle. Remember the general idea in quadrant 2, theta equals pi minus theta reference, and in quadrant 3, theta equals pi plus pi reference. So in quadrant 2, we're going to want getting pi minus 1.115, and that's equal to, we'll jump over to the calculator, so pi minus, and I'm just going to go answer. Okay, so that is 2.026. And then in quadrant 3, you're going pi plus the reference angle. So that's pi plus 1.115. Okay, and then this should be close enough. So this says 4.25, we'll say 7, okay? All right, so this gives us our two angles. So one of the angles is just over 2 radians, and then the other one is 4.257. Now keep in mind that these angles, you can always do this. You can always add 2 pi k, where k is an integer. And same with this. You can always add 2 pi k, where k is an integer. So when we're solving this equation, this actually turns into, what are the possible angles? Pi t equals 2.026, but you could also add 2 pi to that. So what is 2.026 plus 2 pi? So we could also get 8.309, or we can add 2 pi to that as well. And that's going to be equal to 14.592, and we can keep on going and going and going. Now I'm going to go ahead and do something here. I think, let's get one more, but I don't think we're going to have too many of these here, because at some point we're going to get out of our domain. Now if you're going, why are you bothering to do this? I thought you told me the domain was t is in between 0 and 6 minutes, so why do I need any times bigger than 6 minutes? Keep in mind what we've solved for is pi t equals all those times. So t, you're going to have to divide everything by pi. So what that actually winds up doing for you is you're going to wind up getting all these things but divided by pi. Now I've kind of done this the long way. What I could have done is I could have divided this guy by pi, and I could have divided 2k by pi, and that might have been smarter. In fact, that probably would have been smarter, and I'm not so much digging doing it this way, but I've done the work, so I'm going to go ahead and I'm just going to write it out. So I'm just going to take all of these and I'm going to divide them all by pi. So if I divide this one by pi, so this is 20.87. Okay, so this one is 6.644. Okay, so that one's actually out of the domain. So then I'm going to divide, so I'm just going to work backwards here, 14.592. And I'm going to divide that one by pi. And yeah, it's a lot of calculator work, but you just got to do it. Okay, so this one is 4.644. And then that one is in the domain, so that's good. 8.309, and we'll divide this one by pi. And for those of you watching this on YouTube, this is usually where you start to push the right button to skip ahead a few seconds, because you don't really need to watch me work these out. And divide it by pi. Okay, so we get our answers. There we go. Okay, so I'm just going to now, because we've done a lot of stuff, I'm going to highlight these. Okay, so at 0.645 seconds, and 2.645, and 4.644, we can see that we would have had a time equal to those. So those are our solutions. Now we also have another set of solutions, which are the Quadrant 3 solutions. And what I'm going to do is I'm going to make this a lot easier on myself. I'm going to write pi t equals 4.257 plus 2 pi k. And this is going to turn into t equals, and what's going to be a little easier is if I just divide this first number by pi. So that's 1.355, and instead of 2 pi k, it's just going to be plus 2k, where k, of course, belongs to the integers. So just a little record here, all I did was I just divided everything by pi. The reason why this is so much easier is now I can see that my solutions will be 1.355, and then I'm going to add an integer number of times. So I'm going to have 3.355, I'm going to have 5.355, I'm going to have 7.355. Okay, so that's a little smarter and a little easier. All right, so what do we got here when we put it all together? You can see how this is a pretty beastly question here. It's got a lot of steps. And what I finally end up with is I end up with 6 solutions, or 6 times. So putting this all together, therefore, the height equals 40 meters at t equals, and now I can just simply list off all of my times. I guess I can put them in order. 2.645, 3.355, 4.644, 5.355 seconds. Okay, that is a humongous string, but those are all the times. Now let's just take a sec and make sure this does make some sense. Let's go jump over to, let's go open up a Desmos tab and let's have a look at this whole thing. So we started with a function that said y equals negative 25 cosine. Now I'm going to write in here pi. I'm going to use x because that's the variable Desmos expects, plus 29. So here we go. So this is my graph, and I'm going to, set a line y equals to 40. Now, okay, this window is really ugly, so let's just change it. Let's get you out of here, graphic calculator. And let's change this window from x equals -1 all the way till, let's just go 7. Now let's try that again. Let's go 7. Okay, there we go. That's a much better graph. Okay, so this red squiggle is my height as a function of time, and this blue line is, of course, when we reach a height of 40. So we can see our points here. There, there. So why do you get 6 different points? We can see the period of rotation was 2 minutes, so you go up and down once every 2 minutes. So you're going to pass by a certain height. You can go up like this, whee, up, down, up, down, up, down. You're going to pass by that height 2 times every rotation. So we wound up getting all our points. And these look like they all correspond with what we got. So there we go. Now that is a pretty heavy-duty packed question. This is definitely the kind of thing that if I was going to ask you like one question on the test, I would ask you this because it tests so much stuff. So there's that one. Now, if I'm you, I would probably pause the video, go rewatch, and make sure that you are good with this because this is a pretty beefy question. Let's look at some other ones. All right, so other oscillating phenomena. Now, I know we kept talking about Ferris wheels. It's not all about Ferris wheels. Things like tides, even the hours of daylight. You can have a mass hanging from a spring, and it just goes up and down and up and down and up and down. They're actually all described by sinusoidal functions, and a lot of physics really uses this. It describes waves. It describes everything. Well, not everything, but almost everything. In fact, if you're into quantum mechanics, it almost does explain everything. Anyway, let's have an example of daylight. So the longest day of the year is in Whitehorse in the Yukon is June 21st, which has 19 hours of daylight. And the shortest day of the year is December 21st, which has 5.5 hours of daylight. I think I actually looked these up, so true numbers. Determine a sine equation to model the hours of sunlight H as a function of the day of the year D. Assume January 1st to be D is equal to 1 and December 31st to be D is equal to 365, and let's just ignore leap years. Okay, so what I would always do to solve this kind of thing where you're given a description and you need to come up with a an equation, I would actually start by graphing the whole thing out. So I would make just a little sketch here. The hours of light as a function of time. Now, maybe I'll just make this a touch bigger. So we've got this situation here. Okay, let's see if I can draw a straight line. This is my greatest challenge. Okay, a straight line, that's pretty good. So the hours of daylight, it's going to fluctuate between 5.5 hours and it's going to go all the way up to 19 hours. I'm going to call this very first day, that's going to be 1. So that is January 1st. So that's 1. And all the way over here, is December 31st, which is 365. Okay, so we know that somewhere over here, June 21st, we've got 19 hours of daylight, and December 21st, we've got 5.5 hours of daylight. So I've got good news for you and bad news for you. The good news is this is easy to work out, but the bad news is we're going to have to do it manually. What day is this in terms of a number? And then same with December 21st. What day is this in terms of a number? So just a quick little sketch over here. January has 31 days. Scream loudly at your computer if I screw this up. March has 31. I believe April has 30. June also has 30. July has 31. August, I always feel like it should have 30, but I believe that has 31 as well. And September has 30. October is 31 because Halloween. November, I believe, is 30, and December is 31. I don't know who made this silly calendar, but here it is. Okay, so I'm pretty sure that's good. And if we want to figure out where does June 21st fit, so that means June 21st equals, and it's really simple, we're just going to work this out on a calculator. You can't type June 21st in on a calculator, so you have to do it this way. 31 plus 28 plus 31 plus 30 plus 30. And then we're not going to add 31 for June. Oh, hey, look at that. Holy moly. I completely forgot about May. What happened to May? May is also 31, and then June is 30th. There we go. I thought something seemed weird. I didn't think I had enough. Okay, so let's just go back. May is 31, and then finally June is 21. So if you actually work this all out on a calculator, I believe June 21st is the 172nd day of the year. And if you want to work out December, we could keep on adding, but you know what I'm going to do? If December 31st corresponds with 365, then that means December 21st is going to correspond to 355. All right, so at the 355th day, we're going to have a point, and that's 5.5. Whoops, that's 355, comma 5.5. And then over here, so this is like December 21st, and at June 21st, which is at 172, that's going to be a high point, which is going to be 172, 19. So what my graph is going to look like is a high point there, and then it's going to go down like that. And because the Earth is rotating around the Sun in a circular pattern, we're going to have a sinusoidal curve. All right, so now we have to figure out a sine equation. So we have a rough sketch of a graph. The high point at June 21st and the low point at December 21st. So this actually gives us a lot of information. So I'm going to point something out here. First of all, the period of the graph, this might be common sense, but the period is 365 because that's the length of the year. Okay, so 365 days, 1 year, that's how long it takes for the whole thing to repeat itself. So that's maybe just more of a common sense sort of thing. All right, so can we figure out what A is? A equals, remember, now this time I can't just look at it and tell, so I'm going to use the formula. I'm going to say max minus minimum over 2, absolute value. So that's going to be 19 minus 5.5 all over 2. And that's what, 13.5 over 2, so 6.75. B is equal to 2 pi over the period. Okay, so this is going to be a gross number, but that's what it is, 2 pi over 365. C, in this case, what is C? If we look at the official lowest point of the year, or the highest point of the year, we can see that it happens right here. So I'm going to say that there's the max, and this is where cosine starts. So if we're going to use cosine, it starts at 172. So over here, when we're coming up with C, the phase shift is going to be 172 if positive cosine is used, and it's positive because it's starting high. So remember, this is max where positive cosine starts. D, of course, D is equal to, and I'm going to go max plus min over 2. So that's 19 plus 5.5 over 2, so that's going to be 24.5 divided by 2 is 12.25. Okay, so we put this all together. This tells me that the hours as a function of what day of the year it is, the hours of daylight, should be 6.75 times cosine. B is 2 pi over 365. The day of the year, which is D. Up here I realize I put in a T. I guess that should have been a D. D for days instead of T for time. Same idea though. And we're going to go minus 172. Close that all up and we'll add 12.25. And there we go. We've figured out an equation that if I know the actual number of the day of the year, I can use this equation here. So now, of course, B, we're going to use the equation. Determine the hours of sunlight on May 28th. So what number is this? This is January has 31, plus February, which has 28, plus March, which has 31. Now I'm freaking out because I'm on video and I'm doing all this. Let me just consult my calendar. So there we go. So January is 31. June, okay, I know it's a leap year. So February, Norm is 28. March is 31. April's 30. May is 31. Cool. Okay, great. Nothing like that awkward feeling of sitting there going, I'm an adult. I should definitely know this. But something about being on video sometimes freaks you out. Okay, so April's 30, and then of course May is plus 28. So this one here, I could probably even skip using my calculator if I was feeling very clever, but today I'm just not. So we're going to go 31. Okay, so 31 plus 28 plus, I'm just going to go 61 here. I'm just going to do some of the math in my head. Plus 28. Okay, so this, guess, is the 148th day of the year. Okay, so that's what May 128th is. This is D equals 148. So the hours of daylight on the 148th day of the year equals, we should be able to work it out, 6.75 cosine 2 pi over 365, 148 minus 172, close it all up. Okay, so entering that is just a big punching of numbers. 6.75 cosine 2 pi divided by 365, and then multiply by, in brackets, 148 minus 172. Close that all up, and then close up the second set of brackets and add 12.25. When you push equals, you get yourself 18.43 hours. Does that sound about right? Given that the longest day of the year is on June 21st, which is very close to May 28th, and you get 19 hours on June 21st, 18.43 hours sounds about right. Okay. So I'm pretty happy with that. Hopefully you are happy with that as well. We have one more question. I'm going to save that for another part because this is definitely a lot of stuff. These are some pretty beefy questions. So I'll let that soak in and we'll be coming at you later with part 2. Thanks for watching.